Hello everyone and welcome to our first AP chemistry session. I am Jihad Hamasaid, a chemistry teacher, excited to start this journey with you. Today we will be talking about the topics in Unit 1. We will be talking about the isotopes, atomic mass unit, and then the mass spectra of the elements. Let us talk about the isotopes, define the isotope, and then provide the isotope notation for the elements. Guys, the isotope, whenever we mention the isotope in chemistry, we mean having the same an element that has different atoms with having same protons but different number of neutrons. We have got variants of element that having the same number of the proton and electron but different number of the neutrons. Guys, in chemistry, the number of the protons, we call them as atomic number, and the number of the protons plus neutrons, we call them as the mass, atomic mass number. So simply we can say that the same number of the atomic number, we mean the number of the protons, but different mass numbers, we mean different number of the neutrons. Totally with the proton, it becomes the mass numbers. Examples for representation of the isotopes. The element of hydrogen has got 3 isotopes. The protium, which has got 1 proton, 0 neutron, and then deuterium, which has got 1 neutron, 1 proton, and then tritium, which has got 2 neutrons with 1 proton. We will be talking about the isotope notation. The isotope notation can be represented in the way that an element symbol is written. E represent the element symbol, and then Z, as in the lowercase, represent the number of the protons. The A to the uppercase represent the mass number, which are the total number of the protons plus neutrons, guys. How to write the isotope notation for hydrogen, protium, deuterium, and tritium? I'll be writing the symbol for the hydrogen, and then to the lowercase there will be 1 proton for the protium, again 1 proton for deuterium, and then 1 proton for the tritium, because for all of the atoms we have got the same number of protons, but the only difference is in the number of the neutrons, which makes the difference between the different types of those atoms. Here we have got 1 proton, so there is 0 neutron. The uppercase will be 1, and then here 1 neutron with 1 proton becomes 2, and then the mass number here, it becomes 3, because 2 neutrons plus 1 proton. In this sample here we represented that the isotope of different elements. For example, beryllium isotope notation can be written as having 4 protons with 5 neutrons, totally it becomes 9, and then chlorine having 17 protons with 18 neutrons, it becomes 35 to the uppercase, the mass number, and then the atomic number for the sulfur is 16, which is the proton number, plus the 16 neutron, it becomes 32 for the mass number, guys. How about the atomic mass unit, guys? Atomic mass unit is a unit of measurement that measures the mass of an atom of an element. With the scientists, they compared this into 1/12 of the carbon 12 atom. Carbon has got 3 isotopes, carbon 12, carbon 13, and carbon 14, but the most abundant form of the carbon is carbon 12. Mostly the carbon exists in this form of its isotope. The scientists, how they defined or provided this atomic mass unit for to measure the mass of the atoms. You know, guys, the atoms are so small the mass of the neutron, proton, and electrons are not such high masses. In order to use grams or kilograms to measure them, we should use a relative scale to measure the small mass of those small particles, which is the AMU is a most appropriate unit to be measured, to be used to measure the mass of the atoms. Examples for the AMU, the atomic mass unit. For example, oxygen 16 has got 15.9949 AMU, carbon 12 has got 12 AMU, and so on. With the atomic mass unit, which is a unit of measurement to measure the mass of an atom, we have got average atomic mass. Guys, we talked about the isotopes, having several isotopes. When we take the average of those abundance multiplied to the masses of each isotope, we get the average atomic mass of an element. So it represents a weighted average of all naturally occurring isotopes, including all of the isotopes of an element. This can be calculated through the provided equation. Abundance of isotope 1 multiply the mass of isotope 1 plus abundance of isotope 2 multiply mass of isotope 2, and then abundance of isotope 3 multiply to the mass of isotope 3, and so on. Let us provide an example to know how to calculate the average atomic mass for chlorine, guys. We have got two isotopes of chlorine, chlorine 35 and then chlorine 37. This 35 and 37, they represent the mass of the isotope, atomic or mass of those isotopes. We should multiply the mass by the abundance of that isotope, which is 77% of the chlorine exists in this chlorine 35, and then 23% exists in the chlorine 37 isotope. When we add these two together, we'll get 35.48 AMU. That's the average atomic mass of the chlorine. Let us solve more examples, guys. Here we have got three isotopes of magnesium, the Mg24, Mg25, Mg26, with different percentages. As you can see, different percentages for each of them. We should multiply 24 by 0.78. Okay, how to calculate this? 24 multiplied by 0.78, 99, plus 25 multiplied by 0.10, and then 26 multiplied by 0.11. The total we will get 24.32 AMU. That's the average atomic mass of the magnesium. With the average atomic mass, we have got the mass spectrometer. The mass spectrometer is used to analyze the relative abundance of isotopes in a sample. Usually it's provided in the form of a graph like this. It's provided the different isotopes. Each line here corresponded to the having specific isotopes, guys. So we should be able to read this spectrum of each element and answer the following questions. How many isotopes exist? Guys, for answering such questions, we should know that how many lines exist in the graph, there should be the same number of the isotopes. So as you can see, there are how many lines? 7 lines. 7 isotopes exist in the molybdenum. This is the spectrum of molybdenum. And then most abundant one is the tallest one, which is molybdenum 98. As you can see here, the tallest one. And the least abundance is the shortest, which we can say it's molybdenum 94. Molybdenum 94. And then abundance of molybdenum 96. How we can determine that abundance? It's here, the abundance almost we can say it's 17%, molybdenum 96. Why? Because it's between 15 to 20, it's almost 17. Let us answer this question, guys. For the provided spectrum, which shown, what do you think the element will be? For such type of questions, we should use the periodic table to know that the average atomic mass of those elements will be what. But here we'll be calculating the average atomic mass for this based on the graph which is provided. It's 79% here. For 24, the type, the one of the isotope, it has got 3 isotopes. The 25, it's almost 10%, and then 26 also almost 10%, a little bit more, but we can say 11%. So we can say that 24 multiply 0.79 plus 25 multiply 0.10 plus 26 multiply 0.11. These are the abundance and these are the mass of those isotopes as it's given. When we calculate this, we'll get a number 24.06, something like that. That's the most, according to the periodic table. If you look to the periodic table, it's close to the mass of average atomic mass of magnesium, which is 24. And the isotope is more abundant. Which of them is the more abundant? Of course, magnesium 24 is the most abundant, which is we can read through the graph. For the given graph, let us answer this question. Calculate the average atomic mass of boron given the abundance shown. As we have done for the previous one, we should multiply the abundance by the masses. So we'll be calculating 10 multiply 0.2 plus 11 multiply 0.8. Let us calculate this abundance, guys. 11 multiply 0.8, it's 8.8, okay? 8.8 plus 10 multiply 0.2, it's 2, so it will be 10.8 totally. 10.8 AMU, which is D is the correct answer. 10.8 AMU. That's how we solve to find the average atomic mass from the spectrum given. IP real exam questions. Let us solve this question and then we'll end up the session, guys. This question said it has got 2 parts. Said the average atomic mass of neon, it's 20.18 AMU. It has got 2 isotopes, neon 20, neon 22, and then with the mass of each isotope is given. First said, using the information above, calculate the percent abundance of each isotope. Guys, we have got an equation to solve this, which is the average atomic mass equals the abundance of each isotope multiplied to its mass plus the abundance of the isotope 2 multiplied to its mass. So here we have written the solutions. As you can see, 20.18 is given from the question. Abundance, we don't know. We should be calculating the abundance of the isotope of neon 20. This is neon 20, guys. Multiply 19.99, which is the mass of neon 20, and then abundance of the neon 22, Ne 22, guys, multiply by 21.99, which is given as the AMU. mathematically we can say that the neon 20 is x, and then neon 22 is 1 minus x in order to calculate the abundance of x, and then we'll be calculating the abundance of one isotope, and then we'll be using that to calculate the abundance of the other isotope. As I told you, instead of the natural abundance of neon 20, we have written x, and then instead of the natural abundance of neon 22, we have written 1 minus x. Mathematically, we can solve the x. So we got the x is equal to 0.905. How about this is the abundance of, if we change into percentage, it becomes 90.5% of neon 20, which it was x, and then 9.5 remains for the neon 22. That are the abundance of each of those. How we calculated neon 22? 100% minus 90.5%, you'll get the 9.5%. That's the part 1. Part 2 said calculate the number of neon 22 atoms by using the mass of it. Guys, you know that we have got such equation: mole is equal to number of the atoms, number of atom divided by Avogadro's number. So in order to find the number of the atoms here, we have the Avogadro's number, which is 6.022 10 to the power 23, but we do not have the mole. We should convert this mass into the mole of the neon 22, and then we will be multiplying by the Avogadro's number to calculate the number of the atoms. Here we have represented the solution. As you can see that we converted the mass by dividing into the average atomic mass to get the mole of neon, but this is not this is the mole of the neon including both isotopes. How to convert into neon 22 only? We should be multiplying by the abundance of the neon 22, which is 90.5. It's 0.095 mole per 1 mole of neon totally. That mole of neon includes the both isotopes of neon 20, neon 22 moles. In 1 mole of neon, we have got 0.095 moles of neon 20, guys. So here we converted into the mole of neon 22, and then when we convert into the mole of 22, we should be multiplying by Avogadro's number in order to get the number of the atoms. That's the solution of this IP chemistry exam. In summary, guys, we should know that the isotopes differ by the number of the neutrons, and then atomic mass unit standard, use it for carbon-12, the standard, and then mass spectra provide isotope abundance of an element, and then we should be able to calculate the average atomic mass by the provided equation. And finally, thank you for the attendance, and have a nice day, guys. Thank you.